This lecture will be over Chapter 19, Section 3. We're going to discuss electromotive force as well as circuits. So a complete circuit is going to be a conductor in the form of a loop that has providing a continuous current carrying path. So you can see the entire path here in which an electric charge would follow. So the complete circuit carrying a steady current must contain a source of electromotive force, or EMF, symbolized by epsilon. An ideal source of EMF maintains a constant potential difference, A to B, potential difference, and that's going to be equal to E. But every real source of EMF has some sort of internal resistance, and the terminal potential difference then depends on the current. So in other words, this EMF not only is providing this potential difference, but it's also overcoming a little bit of resistance within itself. So the electromotive force is going to be this plus that. So that's probably the best way to think about that. So let's take a look at the section here. Let's kind of see what it has to say. All right, so we've discussed the complete circuit. The path cannot consist entirely of resistance. In a resistor, charge always moves in the direction of decreasing potential energy. There must be some part of the circuit where the potential energy increases in order to be able to complete the path again. So it's analogous here to this fountain. The water is going to come out the top. It's going to cascade down into the basin and then is pumped back to the top for another trip. The pump does work on the water, raising it to a position of higher gravitational potential energy. Without the pump, the water's just going to fall into the basin. It's just going to stay there, and it's really not going to be that interesting. So the same thing happens with an electric circuit. In other words, the battery or other device that does work on the electric charge to bring them to a position of higher electric potential so they can flow through the circuit to a lower potential energy. So it's the same kind of principle. So the influence that moves charge from lower to higher potential is going to be called the electromotive force, EMF. Every complete circuit with a continuous current must include some device that provides electromotive force. They really castigate using that specific term. It's really an energy per unit charge quantity like potential, which I could understand given the description we just had before. The SI unit is going to be the same unit as potential, the volt. A battery with an EMF of 1.5 volts does 1.5 joules of work on every coulomb of charge that passes through it. So batteries, electric generators, solar cells, thermocouples, and fuel cells are all sources of EMF. Each such device converts energy of some form into electric potential energy and transfers it into the circuit where the device is connected. An ideal source of EMF maintains a constant potential difference between its terminals, independent of the current through it. We're going to define the EMF quantitatively as the magnitude of that potential difference. As we see, such an ideal source is a mythical beast like the unicorn, the frictionless plane, and the free lunch. But it's a helpful model. Remember, all models are wrong, but some models are useful. I believe that's Mr. Box there to quote that. So this figure here is a schematic diagram of a source of EMF that maintains a potential difference between points A and B. These are the terminals of the device. Terminal A is going to be marked as positive. It's going to have a higher potential than terminal B, which is going to be marked with a negative sign and a lower potential. Associated with this is going to be an electric field in a region across the terminals, both inside and outside the source. The electric field inside the device is directed from A to B. A charge Q within the source is acted on by a force due to the electrostatic field, or the electric field, sorry. A source has to provide some additional influence, which we represent as non-electrostatic force. It pushes from B to A. You got to get the charge over here somehow. and that maintains a potential difference. The nature of this additional influence depends on the source. In a battery, it's chemical processes, an electric generator. It results from magnetic forces or rubbing plastic on fur. So let's go through the diagram here again. We've seen most of these important parts before. You can see the electric force due to the electric field, and then we've got some sort of non-electrostatic force that's moving this charge that way. When the EMF source is not part of a closed circuit, then this and that are equivalent, and there's no net motion of charge between the terminals. So the potential of point A with respect to B is defined as the work per unit charge done by the electrostatic force on a charge Q that moves from A to B. The EMF of the source is the energy per unit charge supplied by the source during an uphill displacement from B to A. For the ideal source of EMF that we have described, the potential difference is going to be equal to the electromotive force. That's when there's no complete circuit. So now let's throw the switch. We've completed the circuit. And the charge terminals A and B of the source set up an electric field in the wire. And this causes a current in the wire directed from A to B. We're going to use Ohm's law in this particular case. The current is described as the electromotive force, which is going to be equal to V from A to B, and that's equal to IR. Again, this is for an idealized setting. So we can see the current or the electric field going from the positive to the negative terminal. And when a real, as opposed to ideal EMF source is connected, then this voltage and thus this force is going to fall. So that this non-electrostatic force is going to be greater than the force to the electric field, and this does work on the charges. So when a charge Q flows around the circuit, the potential rise in electromotive force as it passes through the source is numerically equal to the potential drop as it passes through the resistor. Once we know these values, then the relationship determines the current in the circuit. Current is the same at every point in the circuit. You don't see current bunch up. It doesn't work that way. So real sources of EMF don't behave exactly like the ideal sources because charge that moves through the material of any real source encounters resistance. And for this particular case, for the EMF, we're going to call that internal resistance of the source. And we're going to define that with a little r. If this resistance behaves according to Ohm's law, then R is going to be constant. The current through that has an associated drop in potential equal to I times little r. Therefore, the terminal potential difference is going to be the electromotive force minus the current times the internal resistance. This is going to be called the terminal voltage, and it's going to be less than the electromotive force because the term IR represents the potential drop across the internal resistance. The current in the external circuit is determined by this. Combining that relationship with this, we're going to find out that the current is going to be equal to the electromotive force divided by the sums of those resistance. So, summarizing, a circuit is a closed conducting path containing resistors, sources of EMF, and probably other circuit elements. What we're going to see in equation 19.7 is the algebraic sum of the potential differences in EMF around the path should be 0. Also, current in a simple loop is going to be the same at every point. And this is because charge is conserved. If the current were different at different points, then you would see accumulation of charge, and we don't see that. This figure is going to show the symbols usually used in schematic circuit diagrams, and we're going to use these symbols in most of the circuit analysis in the remaining parts of this chapter. So you can see the wire with negligible resistance, then a resistor, positive terminal, EMF source, then you got something with internal resistance, you got a capacitor, open switch, closed switch, a bulb, a voltmeter, an ammeter, and the ground. So you got a few problems there to work through.